People used to drink from whatever water source was handy, without giving much thought to its safety. Technological advances were aimed mostly at making access to water more convenient. After centuries of progress, finally, in the late 19th century, a remarkable thing happened. People were able to turn on a faucet within a building, and water would flow out. This welcome convenience brought with it an unintended consequence. You see, this same plumbing that brings good water into the wash basin is also a means by which contaminants can flow back into the public water supply. And it wasn't long until this happened. Incidents of cross-connection began to be reported as early as the turn of the century. In 1933, at the Chicago World's Fair, 98 people died and thousands more were hospitalized when amoebic dysentery and sewage backflowed into the water mains. In 1944, in Los Angeles, harbor water was pumped into the fresh water supply of a ship. In outbreaks of Legionnaire's disease, beginning with the 1976 incident at a Philadelphia hotel, backflow was strongly suspected to be a contributing factor. Every year, incidents of cross-connection cause inconvenience, illness, and in all too many cases, death. For us to minimize these cross-connection problems, we must first better understand how they happen.
Come back here!
Water always seeks a lower level. To get there, all it needs is something like this. It's called siphoning, a common phenomenon wherever fluids and gravity are found. Now notice there's another hose in this water, a hose that's connected directly to the public water supply. Now, what would happen if the water was turned off for, let's say, repairs on the water main? The dog water would be drawn through the wash basin hose and back out through the faucet just like it flowed through the siphon hose. The dog water now would be in the water main, or public water supply. So, where might that water end up?
No, every time you read a newspaper, there's something else you're not supposed to have. And almost always it's something I like. Seems like the only thing that's safe anymore is water.
Oh. Marge, I think there's a flea in my water.
A what?
A flea in my water.
Oh, my. Look at what's in my glass. Oh, my God, that came out of my faucet.
Though unpleasant, fleas in drinking water is not one of the more dangerous consequences of a cross-connection. Consider this. What would happen if pesticide or fertilizer residue collected in this sprinkler head? Nothing, most of the time. Except if a construction crew broke a water main, water pressure would then drop and the pesticide could be siphoned back into the public water supply. Now, this could be fatal. But fortunately, it is easily prevented with a vacuum breaker. A vacuum breaker is basically an air vent, installed in a fitting that's mounted higher than any other point downstream. There are two types of vacuum breakers, an atmospheric and a pressure vacuum breaker. Though mechanically different, they work on the same principle, that their air vent is forced closed by the pressure of water flowing through the assembly. But what would happen if, say that construction crew broke a water main again, or a fire hydrant was opened? The inlet valve would open, letting air into the line and breaking the vacuum so that no water or pesticide could be siphoned backwards through this vacuum breaker assembly. It's simple. It works. But what would happen, say, at a tall building where the water was under pressure? Buildings like these need booster pumps to get water to the top floors. The booster pump can create pressure in the water pipes that may be greater than the pressure in the public water mains. So, to prevent this greater pressure from creating backflow, at the service connection of some buildings, you'll find a double check valve assembly. Water pressure forces spring-loaded valves open in the normal direction of flows so everyone can wash their hands and flush their toilets. But if for whatever reason the water became polluted in the building and the pressure from the booster pumps ever created the potential for backflow, look what would happen. The one-way check valves would be forced closed. So even in situations where one of the check valves was held open by, say, sediment or rust particles caught on the valve seat. Only a small amount of backflow could ever get through. A double-checked valve assembly can only be used to protect against aesthetically objectionable materials. Well, that is, not dangerous to our health. At a hospital or a manufacturing plant, materials that could be hazardous to health could backflow. Here, a reduced pressure principal assembly is necessary. This assembly also contains two check valves. The difference is that they are augmented by a differential pressure relief valve. This spring-loaded relief valve is forced closed by normal water pressure, so water flows right past it. But look what would happen if, for whatever reasons, the water is back-pressured through a leaking second check valve. Well, the differential pressure relief valve would open, creating an opening in the center chamber, draining the water completely out of the assembly, and thus never reaching the first check valve. Any substance that somehow made it past this check valve would now flow harmlessly through the opening and completely out of the assembly. This reduced pressure principal assembly is almost fail-safe. However, any mechanical device is subject to failure, so an extra measure of protection is necessary in certain applications. Anytime we're dealing with sewage, there may be highly toxic chemicals or lethal viruses present. In this situation, the only acceptable backflow prevention is a complete break or an air gap. Water flows through the air into a reservoir, thus ensuring the hazardous material never reaches the clean water supply. Air gaps are simple, effective, and you see them applied every day. Remember that old-fashioned bathroom I showed you earlier? Look what happens when the bathtub is filled up. This water that's now in direct contact with the public water supply is also in direct contact with the drain. And we all know where that goes, the sewer. So what have we done? We've just cross-connected the sewer with the public water supply. Well, they don't make them like they used to. If you fill a modern wash basin all the way up, you'll find that the water level never reaches the nozzle of the faucet. Now there, that's an air gap. And for years, plumbing codes have mandated that every sink must have this air gap. Backflow prevention is now so effective that most people think nothing of taking a drink from whatever water source is handy without giving much thought to its safety. Convenient? Yes. But it has created an unintended consequence for those people who are trying to protect us from the hazards of backflow.
I've never heard of these kinds of problems you're telling me about, and we've certainly never had them here.
Well, your current building already has the necessary assemblies to prevent backflow problems. And that's all we're asking you to do in your new facility.
How do I know they're really necessary?
Human life's at stake, so we have to take reasonable precautions.
So what's the least expensive assembly I can buy?
It's not that simple. The assembly must be matched to the application and its potential hazard.
Knowing which assembly to use in any specific application means that our technology must be augmented with a system for establishing standards. No problem. There are volumes on the subject. There's even a standard reference source called the Manual of Cross-Connection Control, published at the University of Southern California by the Foundation for Cross-Connection Control and Hydraulic Research. Local governments around the world refer to this manual in their plumbing and building codes. But what good are standards on paper without an impartial means to certify which assemblies measure up to those standards? It's no small job certifying every backflow assembly on the market, but it's done right here at a University of Southern California laboratory operated by the same foundation that publishes the Blue Manual I was telling you about. This is the only lab in the world that tests assemblies both in the laboratory and in the field. Assemblies that pass are included in the list of approved assemblies. So now, with technology, standards, and impartial approval, you may assume that we have everything we need to control backflow problems. But you wouldn't be quite right.
All of our people are well trained and very careful.
I have no reason to doubt that, but there's usually no way to even tell that you have a backflow problem until some damage has already been done.
Well, still, you're asking me to spend a lot of money.
I'm asking you to conform to existing codes.
Well, how exactly are you going to know what I install in my plant?
Backflow prevention is an unusual sort of activity in that when you work hard and do everything right, nothing happens. And to keep nothing from happening, regular inspections are critical.
In order to determine the type of backflow protection that's needed, we have to establish a degree of hazard. To do this, we need to make an on-site inspection of the water-using facility.
Here is where knowledge from the laboratory is conveyed into the field so that cross-connection specialists know what to look for and know how to enforce the standards that keep our water safe to drink.
It's very important during your testing of the backflow prevention assembly that you read your gauge accurately. The values that you're going to be interested in...
Field technicians are also trained. They help ensure that once installed, backflow assemblies continue protecting us from pollutants and contaminants.
Then once you have completed the test, we will be taking those values and analyzing that for troubleshooting.
So now, we've seen how technology, standards, impartial approval, regular inspections, and training all combine to help meet a very basic need.
You know, that's something that never ceases to amaze me. Safe drinking water is something everybody understands.
Sure, but anything that increases construction costs, I have to look at very critically.
All I'm asking you to do is consider the consequences.
Such as?
You can lose a lot more than money by cutting corners.
Daddy! Oh, hi, honey. Just a second, huh? I guess we have gotten used to drinking whatever comes out of the tap without giving much thought to its safety.
Mm-hmm, and it's nice we can do that, don't you think?
I think we agree. Come on, honey. Mommy's waiting.
When our public water supply and the health of our children are at stake, I think we can all agree that in addition to convenience, we all want the assurance that we can drink the water from any tap without having to worry about its safety. Now, if you'll excuse me, all this talking has made me very thirsty.
Welcome to the New England Water Works Association television classroom. This video has been produced in response to the growing need for professional cross-connection control surveying. Under the provisions of the Federal Safe Drinking Water Act, water providers are responsible for water quality from the reservoir to the tap. The existence of cross-connections represents a real hazard to water quality. In order to ensure water quality throughout the distribution system, the water system manager should initiate a cross-connection control program to evaluate how the consumer uses the water once it enters the building, and to ensure that the distribution system and all consumers are adequately protected. This tape will introduce you to cross-connection control surveying techniques and will also discuss the preliminary work needed to implement a survey program. It will show some of the more common, typical cross-connections, discuss degrees of hazard and cross-connection control devices and assemblies, as well as recommend proven procedures for conducting a survey, and culminate in an actual survey of a public facility showing examples of solutions throughout this process. To establish a cross-connection control program, it should be determined what type of cross-connection control program is desired: containment, internal protection, fixture outlet, or total protection involving all three. A containment program isolates the building from the public water supply by using a testable backflow prevention assembly at the water meter. This assembly protects only the public water supply and not the water used inside the building. Internal protection places testable backflow assemblies on the potable feeds to high-hazard installations inside a building, such as boiler feed lines. Fixture outlet protection is implemented when devices are installed at the last free-flowing outlet, such as a slop sink. When planning a total cross-connection control survey program, all of these methods of protection must be included. There are many backflow prevention devices and assemblies available that can be utilized at cross-connection points. The degree of hazard determines the selection of the appropriate backflow prevention device or assembly. If a cross-connection constitutes a relatively low hazard, appropriate protection could be afforded by a double-check assembly, pressure vacuum breaker, or other device as indicated by community, state, or regional regulations and conditions. The term low hazard applies to non-toxic substances. If a cross-connection constitutes a high hazard, recommended protection is a reduced pressure principle backflow prevention assembly when creation of an air gap is impractical. The term high hazard applies to toxic substances. Remember, addition of chemicals for any purpose increases the degree of hazard to potable water. Prior to initiating a physical cross-connection control survey program, it is strongly recommended that a local cross-connection control ordinance should be established and legally adopted. This document gives the local water utility the legal authority to conduct surveys, and it compels each water user to comply with the findings. These local ordinances may be reinforced and supported by state cross-connection control regulations or guidelines and by the Federal Safe Drinking Water Act. There are several key preliminary steps for implementing a cross-connection survey program. You should develop a comprehensive cross-connection control manual that has the legal backing of local ordinances, state and federal regulations and guidelines. Notify appropriate community departments and officials concerning the program and its purpose. This list could include the health department, police and fire departments, and town or city clerk's office. Notify state officials and state agencies of the intent of the town or city to conduct cross-connection control surveys. Obtain the support and cooperation of local plumbing inspectors. They should be involved in the groundwork stages and be available for consultation. Recruit and ensure training of professional cross-connection survey personnel. Educate all water utility personnel regarding the potential health risks of cross-connections and the basic components of a cross-connection survey. Issue news releases to radio, TV, and the print media to help inform and educate residents about the impending survey program. Assess potential hazards. Start with a meter list and prioritize potential hazards such as car washes, mortuaries, hospitals, plating plants, and so forth. These high-hazard installations should be the first sites inspected. Determine if the survey will be conducted announced or unannounced, and if appropriate, security clearances are necessary. It is strongly recommended to conduct announced surveys. Determine if the survey will be conducted by 1 or 2 survey specialists. Surveying in pairs, which is recommended, enhances the opportunity to detect cross-connections. Require that basic safety considerations and equipment be utilized. Upon completion of these preliminary steps, it is time to define how the survey will be conducted. The survey begins with the scheduling of a meeting with the responsible person of the facility, where the team will provide a concise introduction and overview of the survey. The discussion should include why and how the survey is being conducted, what authority has been granted to perform the survey, and a request for access to all areas of the facility. The survey team should ask questions relating to the operation of the facility and how the public water supply is utilized. The answers will guide the survey team through the facility and the survey process, assisting them in noting key areas to be inspected. The survey team should request drawings depicting the facility's plumbing system. In older buildings, problems arise with as-built drawings because it is difficult to determine if they have been kept up to date. In new installations, as-built drawings may have great value and will show the survey team the extent and detail of the potable water supply plumbing system and how it is used. Ask the facility representative what operations are conducted in the facility and determine if inherent hazards to the potable water supply exist. For example, some fish processing facilities use an iodine compound as a sterilization medium. It is pumped throughout the plant to sterilize process machinery, workers' hands, and instruments. An electroplating facility uses process tanks containing highly toxic chemicals. Water is added to these tanks from below or above the flood rim. Those filled from below constitute a cross-connection. The survey team needs to ask questions that will provide this type of information. The following are other typical questions that should be asked. Is the potable water supply directly or indirectly used for manufacturing processes within the facility, such as chrome plating tanks, acid baths, bleaching and dye vats, or photographic laboratory equipment? Does the boiler system utilize chemical additives? Chemical additives are commonly used as descalants, deoxidizers, and corrosion inhibitors in commercial or industrial boilers. Are air conditioning cooling towers utilized? Virtually all employ algicides, fungicides, and other biocides. Is there a water saver in use? A water saver is a system which is used to cool and reutilize processed water. This is customary in many commercial applications. Water savers generally utilize algicides, fungicides, or other biocides in addition to defoamants. Is fire protection water supplied by the potable water system, and are antifreeze or foam additives used? Is there another water supply in use other than the potable system? Does it in any way connect to the potable water plumbing system, creating a cross connection? Does the facility have any type of irrigation system? If so, are chemical fertilizers added? Does the facility require a non-interruptive water supply? This is extremely important. If the facility has the need of a constant water supply, such as a hospital, then the survey team must take note. This type of facility will require the installation of parallel or dual backflow preventers as containment assemblies. In the course of the interview, the survey team must establish if a containment assembly is already installed. Make certain the responsible person knows what containment means. Remember that the survey team is not limited to these inquiries. In the course of the interview, other pertinent issues may arise requiring additional questions. The interviewer, by thorough, in-depth questioning, largely determines the overall quality of the survey. When these preliminary questions have been answered, the survey can begin, systematically visiting and inspecting every water usage on every floor in every building of the facility. Again, safety considerations are paramount. The safety checklist should include a hard hat, safety glasses and shoes, earplugs for high noise areas, a battery-powered flashlight, not an electrical trouble light, oxygen sensing equipment for pits, and a wooden or fiberglass ladder. While there are many possible cross-connections in commercial and industrial facilities, a hospital was selected for this training video because it provides significant examples of typical cross-connections. Once the survey team has met with the hospital's director of facilities operations, reviewing all key information such as as-built drawings and the critical questions regarding water usage, the actual survey of the hospital begins at the water meter and will follow the water flow through the facility. This hospital has a sole incoming potable water supply located in the boiler room. Containment protection is afforded by the installation of parallel reduced pressure principle backflow prevention assemblies, which meet all regulations and guidelines. This installation allows independent shutdown of each assembly for testing and repair, while still maintaining water supply to the building. Since this hospital already has containment assemblies on a potable water supply, a photograph or sketch of the installation is not necessary, but may assist in preparing the final report. Photographs or sketches are useful in the event that there are no containment valves present and a decision is later made to install one. The sketch or photograph assists in finalizing technical drawings or sketches for subsequent backflow prevention assembly installations. When the final technical drawings or sketches are presented to the building owner, they should include the recommended choice of appropriate backflow prevention assembly based on the degree of hazard. Any specific requirements regarding installation, such as state and local codes, should be referenced. The survey next addresses the water feed to the boilers. The hospital's plumbing system has a separate line for all processed water, which includes the boiler supply. Through the interview and inspection process, the survey team determined that the boiler water contains toxic chemical additives, specifically descalants and deoxidizers. Further discussion and inspection by the survey team revealed that the same processed water line supplying the boilers also feeds the air conditioning cooling tower, and that chemical additives are utilized. Algicides, fungicides, and other biocides are injected into the air conditioning cooling tower water via the pump system shown here. Due to these additions of toxic chemicals, both the boiler and the air conditioning cooling tower water are considered high health hazards. The hospital has installed a reduced pressure principle backflow prevention assembly on the processed water line, which affords protection from all uses of processed water, including the boilers and air conditioning cooling tower. Because the survey team determined that all water feeds to the boiler and air conditioning cooling tower came from this processed water line, there was no need to look for further protection in our hospital survey. However, in many installations, the boiler would be on a separate feed, as would the air conditioning cooling tower makeup supply, requiring separate assembly installations for protection. Next, the fire protection system is examined to see if any cross-connection protection is afforded other than the alarm check. The survey team must remember that fire protection systems may contain black or stagnant water on the downstream side of the alarm check. Chemical additives may also be used in fire protection systems. The survey team must also be concerned with the presence of Siamese, or fire hose connections, which are usually located at street level, protruding through an exterior wall of the building. These connections to the downstream side of the alarm check are used by the fire department to augment the standard fire protection system with either potable or non-potable water. Because of the presence of Siamese connections and the possibility of contamination by black or stagnant water, the double check valve assembly, seen here, provides the hospital with the protection desired by the water utility. In surveying other facilities, beware of possible chemical additives or antifreeze in the fire protection system, which may necessitate the installation of a reduced pressure principle backflow prevention assembly as the appropriate assembly for a high degree of hazard. During the interview, the survey team learned that an irrigation system is present at the hospital. The survey team should examine the type of irrigation system used. Does the system use chemical additives such as liquid fertilizers? In the absence of highly toxic chemical additives, protection can be afforded through the use of a pressure vacuum breaker. However, the utilization of toxic chemical additives would necessitate the installation of a reduced pressure principle backflow prevention assembly. In our hospital survey, a reduced pressure principle backflow prevention assembly is installed to provide the highest level of protection, even though chemical additives are not utilized. The above-grade installation allows the assembly to operate properly, avoiding malfunction due to submersion in below-grade installations. Cafeterias and kitchens have many cross-connections, such as ice machines, post-mixed beverage machines, disposals, sanitizing equipment, dishwashers, and hood washers. The survey team's visit to the hospital's cafeteria and kitchen found that the ice machine, shown here, has a water feed entering the top of the machine. These small top-loaded ice machines represent no hazard, provided that an air gap separates the machine's internal reservoir from the potable water supply. Verification of the existence of an internal air gap may require visual inspection following disassembly of access panels, or may be determined through examination of manufacturer schematics if available. If the machine is bottom-loaded or no schematics are available and inspection is not possible, a backflow prevention device or assembly should be installed as required by regulations. Some beverage machines are post-mixed, utilizing a water supply connection to produce a carbonated beverage. Post-mixed beverage machines, both coin-operated and self-service, can be extremely hazardous in the event of back pressure and a failed check valve condition. Carbon dioxide in the soda water can react with the copper tubing to produce toxic copper carbonate. The beverage machine in this survey is connected to the potable water supply and is not protected. Contamination of the water supply could result. The survey team will recommend that a special stainless steel backflow preventer designed for carbonated beverage machines be installed. Most large cafeterias and kitchens incorporate an automatic dishwasher utilizing soap injection. The survey team must look for atmospheric vacuum breakers and determine if the shutoff to the atmospheric vacuum breaker is located on the upstream side and the soap additives are injected below or downstream of the atmospheric vacuum breaker. The automatic dishwasher in the hospital had properly installed atmospheric vacuum breakers. The survey team found one of the hospital kitchen sinks with soap injection incorrectly installed. Questioning by the survey team established that this type of installation by an outside vendor was an ongoing problem encountered by hospital facility services. The survey team will recommend the installation of an atmospheric vacuum breaker and the relocation of the soap injector. Atmospheric vacuum breakers must be installed higher than the actual water outlets and in accordance with plumbing regulations. The survey team also examines every slop sink. The slop sink shown in the hospital survey provides excellent protection with a built-in atmospheric vacuum breaker. It is important to check every slop sink on every floor of a facility. The survey should include an examination of all laboratories. In this hospital, many different types of laboratories are present. The entire laboratory area is contained through internal protection with separate reduced pressure principle backflow prevention assemblies on the cold and hot water supplies. Since laboratory gooseneck faucets are a hazard, this protection is augmented by atmospheric vacuum breakers at each outlet. Each facility has different specific hazards. In the hospital survey, specific hazardous areas have been examined, such as the autopsy room, operating rooms, recovery rooms, sterilization chambers, dialysis machinery, and similar equipment areas. All of these areas represent hazards and should be isolated from the potable supply with containment assemblies and fixture outlet backflow preventers where appropriate. We will review two examples of hazardous areas in our hospital survey. First, the autopsy room, similar to the laboratory, is contained through internal protection by separate reduced pressure principle backflow prevention assemblies on the hot and cold water feeds and augmented by atmospheric vacuum breaker fixture outlet protection throughout the room. Second, in the radiology suite, the water feed to the X-ray developing equipment is protected by a reduced pressure principle backflow prevention assembly. Since both X-ray and autopsy represent high hazard areas, the choice of reduced pressure principle backflow prevention assemblies augmented by atmospheric vacuum breakers is appropriate. The survey team found this level of protection consistent throughout the other specific hazardous areas previously mentioned. Following completion of the survey team should return to the facility representative and present a summary of the survey. This provides immediate results and discussion of the facility's needs for cross-connection control. If any existing protection was found, it should be noted. Acknowledgement of existing correct installations may serve as positive reinforcement and encourage an atmosphere more receptive to recommendations concerning additional protection. Following the meeting, the survey team will translate field notes into a formal written presentation combined with appropriate sketches. The survey team should submit the final report to the facility representative and the local water utility. If the installation of backflow prevention devices or assemblies is recommended, these recommendations should be based on the degree of hazard. Any specific requirements regarding installation, such as state and local codes, should be referenced. Compliance deadlines and the notification process will also be determined by state and local requirements. Unforeseen contingencies occasionally present problems to the cross-connection control survey specialists, especially if the survey is unannounced. The survey team's presence can be unwelcome and entrance may not be permitted. The survey may also be terminated if it is perceived as an invasion of privacy or a threat to proprietary information. If the survey team feels that they have not been given full access to any area where water is supplied, this will be noted in the written report, and installation of containment assemblies should be required. Security concerns do exist, particularly in defense installations, and this has to be anticipated accordingly. The survey team must remember they are working on private property. Advance permission with confirmation prior to the survey is strongly advised. This concludes the survey. You are encouraged to review all or any part of this tape at your own pace. It should serve as resource material and as a complement to formal training. What follows is a list of facilities with possible cross-connections. Technological developments continue to produce potential cross-connections, and the list will expand. The cross-connection survey should be conducted following thorough planning and with a checklist in hand. Common sense approaches to piping systems prevail throughout the survey. Some recommended reference documents containing more detailed lists of cross-connections in various facilities and their suggested remediations are the U.S. EPA Cross-Connection Control Manual, the University of Southern California Cross-Connection Control and Hydraulic Research Manual, the American Waterworks Association Cross-Connection Control Manual M14, the National Plumbing, Heating, and Cooling Contractors Cross-Connection Control Manual, and the Pacific Northwest Section AWWA Cross-Connection Control Manual. We hope you enjoyed our video presentation. Thank you for attending the New England Waterworks Association television classroom.